So once I bring up what?
Once you bring up PowerPoint, it should full screen onto that.
Yeah. Okay. That's great. Okay. So, ladies and gentlemen, today we had two things due, or one thing due for the take-home exercise. I'm actually going to defer the discussion. Thanks a ton, Merlin. Defer to the discussion of that until next time, so we can have it in a way that discusses both that take-home exercise and the one due Thursday, which focuses on the same model, although a different aspect of analysis with it. So today's presentation, I'm going to be talking about a class of models that you haven't previously encountered explicitly, but which is very, very important element of modeling, a very important sort of strain of modeling. And that concerns what I'd like to term stylized models. Other modelers term them more theoretic models or mechanism models. These are models whose job is to serve as thinking tools to help understand the implications of how very simple assumptions involving just a few mechanisms within a model, say how people choose where to live and choose when to move, or mechanisms involving how a few set of cells in one area influence cells in a neighboring area, how those mechanisms, what the implications of those mechanisms are for the pattern seen more generally within the system, and particularly for the behavior of the entire system. Sorry? It's broadcasted, yeah. It's not showing? Mumble, okay. It says stop broadcast, so it thinks it's... Oh, I see. Mumble, okay. Oh, okay. Here, I know what we have to do. Sorry. Thank you very much. Now we have infinite slides shown. Is that good? Okay. Great. Okay. Is it showing something now? Okay. 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 We're in good shape then. So these are models. Thanks, Hayden. These are models which help us think through how a few simple mechanisms put together yield behavior for a system as a whole. We're dealing here with, again, systems where the whole is greater than the sum of the parts. That's what we're dealing with in this class. Nonlinear systems being the case in point. With these systems, we can't reason about the behavior of the whole by simply reasoning about the behavior of each piece and totaling it up. It doesn't work that way. We have very distinct behaviors for the system as a whole. It's a hallmark of nonlinearity that we see this distinction between the behavior of the system or the function as a whole and the individual pieces. And when we're dealing with systems like that, whether they're complex engineering systems, systems involving software project teams, systems involving competition, or involving the spread of infections, or other aspects of health, or of industrial processes, or what have you, we often build models as thinking tools, models as tools to help us think through what are the implications of making these assumptions in terms of the behavior that I see. And they can help us speed up our learning process by reasoning through more quickly how a couple small mechanisms interact to yield overall behavior. And stylized models are not meant to depict a particular situation in the world, but rather to address exactly that problem. How do just these couple of mechanisms together lead to behavior that we observe for the system as a whole? So they abstract away from the vagaries of particular situations, and they focus on a few defining essentials. So we're going to be looking at a model, for example, that has to do with segregation, in particular segregation of people who look differently. And this model is not about, it's not about Detroit, it's not about Los Angeles, it's not about Chicago, where we see large patterns of segregation. Rather, it's about a way of investigating segregation more generally, in a more sort of abstract way that might help understand how certain patterns combine to yield patterns of segregation that we might see in the world. Okay, so we're going to be talking about these models, particularly in the context of what I term spatial embedding, where we place agents in space. The past few lectures, we've talked about embedding of agents in networks, what I'd call topological embedding. Topological embedding has to do with who's connected to whom, which two people are connected by a network, and how does that impact the dynamics of the model, the behavior over time of that model. Here, we're going to be dealing also with interactions between an agent and their environment. There, we dealt with networks. Here, we're dealing with space. We're dealing with the fact that certain agents are co-located or located next to each other, or near enough to each other to transmit infection or to transmit influence in terms of norms or transmit a rumor or what have you. And we're going to be seeing how we can build models of this sort that include agents in a certain context. And we're going to particularly look at this today in the context of these stylized models, these very, very simple models. And if time allows, and I recognize we started a bit late because of technical issues up here, but if time allows, we're going to look at two cases. We're going to look at a case where we have agents in space that are situated at a fixed location, and then a situation where agents can move about, agent mobility. Okay? It's possible that will have to be deferred to next time. Next time, we'll be further looking at agent mobility in the context of GIS space, meaning geography, okay? Putting people in a specific geographical context. That's next time. Okay, so when we think about agents at certain locations, capturing their location is actually really important for certain needs. For expressing certain types of essential dynamics between agents. Say, the fact that two agents need to be co-located to have a certain type of contact, to share a needle, or have a sexual contact, for example. They need to be nearby each other. So insights into transmission. There's other phenomena, too, where we might want to capture influence. The fact that someone could be contaminated by soil at a certain location, for example, or could contaminate a surface with an infectious disease because they're nearby that surface. We might be interested in explaining spatial reference modes. In other words, reference modes where we see certain patterns in space. And a spatial model can help reason about that. We might be interested in understanding how the structure of the space impacts agent behavior over time and their ability to maneuver within that space, for example. And interest in how that space limits transmission from one region to another through what's called percolation, where it needs to go from A to B and B to C and C to D and D to E in order to finally get to F. Okay, and we're going to see next time that spatial embedding can allow for GIS integration. Now, in this package, which we're using in this class, there's three basic types of spatial embedding that we're going to be examining, and these are not merely accidents of the software. They mirror three traditions of modeling at the agent-based level, particularly. One is continuous embedding. Here we have agents embedded in a continuous space. By continuous space, I mean it's their location in two different directions, and in fact in three, if you want to allow it, is a continuous variable. So, for example, I can be, 32.3 miles east and 42.4 kilometers north of a certain location. Okay. Here, there's going to be no physical exclusion. Two agents can be basically on top of each other without problems in any logic. A second type of spatial embedding is a subset of that. It's continuous, but it's specifically in GIS space. So here we have latitudes and longitudes very specifically. It's not abstract, just distance from some point, but rather you're situated in a geographic environment. You're in Saskatoon, or you're in Prince Albert, or you're in Vancouver or what have you. And you have a certain heading, a certain direction you're facing, and in addition to latitude, longitude. And then you can interact with information about the space around you. We're going to be going into that a lot next time. The final form of embedding that we're going to see is the one we're going to explore today, which has to do with a situation where we discretize space. What do I mean by discretize space? Can anyone say? If we say we discretize like a variable, what does that mean? Or that it's a discrete variable? Does that mean it doesn't spread rumors, that it keeps secrets? What does it mean? Yeah, it's countable. Beautiful. My hat is off to you. Bingo. Yeah, so it's countable. We have a defined countable set, possibly infinite, possibly finite, of possible different values of it. This is in contrast to a continuous variable where we can have an uncountable number of possible values. 3.14, 3.141, 3.1415, 3.14159, 3.151. Well, I won't go on. But the point is, there's an uncountable number. It's too many to map to the integers. Here, with the discrete count, we divide it up into a defined quantized set of possibilities. And reflecting that, we divide things up into columns and rows, okay? And there's going to be physical exclusion, only 0 or 1 agents in a cell at a given time. So reflecting that, I'd like to open up any logic here, and I'd like to call up a model that will illustrate this, okay? So if you go get your AnyLogics up, you'll find that on the welcome screen, don't rush past it this time, there's a thing called Open Examples. Now, if some of you already have AnyLogic up and you want to do help and go to example models, you can also come back to this screen, okay? And within this screen, we're going to see there's a wide variety of models included, and we're going to be exploring 2 of them today. Both of them involve situations of agents in a discrete space, meaning a space quantized into columns, defined columns and rows, countable numbers of possibilities. I can be a row 1 or row 2 or row 3, and I'm not between the 2, okay? So in the example models area, over here on the right-hand side, examples, you will find one called The Game of Life, which sounds like a very ambitious game to have. So I'm gonna click on it. I'm gonna load that model in. Okay. I'm loading that model in here, and you'll notice that we have this defined within main to show a space, and there's actually a small marker there in the upper left that we're going to talk about. And I'd like you to run it. So I'd like you to go to simulation run, okay? And I'd like you to go run the model. And as I said, we have rows going down here on the vertical axis and columns on the x-axis. And within this game, invented first by a mathematician Conway in Britain, what we have is each location here is in one of 2 states. It's binary. It's dichotomous. Either it's alive or it's empty. It's either a living cell or it's an empty space. And over time, we're going to have evolution of different areas within this space reflecting the rules. No agent moves here, but you can have emergent patterns that move. We can have, just like we could have a wave that moves over the surface of water without each particle of the water moving with it. It's a phenomenon, it's a collective phenomenon. So it is with this model. We have these collective phenomena associated with different elements. And in fact, by clicking on the space, you can you can cause changes to the space that will evolve over time. And some of you may enjoy doing that. So here we're going to see collective impact of certain simple rules on the evolution of space. And we're going to go into the rules behind this space in just a few minutes here, okay? The rules that are evolving here over time. With each cell being either living or dead, no cell moving, but giving rise to things which do move, like this little spaceship here that was moving across the space, okay? So how is this captured? Well, it turns out within any logic, if you go poke around, we have within main, some of you, I'm telling you this because some of you may want to pursue this in your projects, in space and network, you'll notice that this is set to use a discrete space here under the space and network properties of main. And specifically, there's 100 rows, 100 columns, okay? And more than that, each agent is defined as having 8 neighbors in this space. North, south, east, west, northeast, southeast, southwest, and northwest. Okay? So they have 8 neighbors, the 4 cardinal directions, and additional neighbors. Okay? Alternatively, if we wanted to, we could simulate the same game, or a similar game with 4 neighbors. Here, individuals will be only considered to have 4 possibilities of neighbors, and what we would see is a very different dynamics associated with that space. A different dynamics because it's a much harsher environment, it turns out, in terms of the rules to survive. So I'm going to shift it back here in main to consider 8 neighbors, but be aware that sometimes we run these simulations with just 4 neighbors. I have neighbors in my north, south, east, and west. Okay, and we indicate the breadth and width of the space, and then that it's discrete. Okay, alternatively, we could specify a continuous environment here, in which case we don't have a choice of rows and cells. Rows and cells are only for discrete environments, where we have these discrete locations in X and Y. In a continuous environment, we just have arbitrarily fine distinctions about our location in X and Y space, much like we will with GIS in terms of where we'll have, okay, I'm going to have to undo that, where we'll have latitudes and longitudes. Okay, so we're going to be operating today in the discrete space, and I've asked you to load in the game of life. So this game of life was invented in 1970 by, I think it was Stephen Conway, adapting ideas from a pioneer of computing called von Neumann. Does anyone recognize that name, von Neumann, in conjunction with anything else in computer science? Yeah? What else do you remember the name from? Yes, he did game theory, stuff reasoning about, you know, if I'm involved and another actor's involved in a game which involves successive steps, how are my actions shaped by knowledge of how that actor or adversary might behave, and how is that actor's action shaped by mine? So very good. And that's of use in reasoning about strategies for example, game playing in a game of checkers or chess or something like that. Where else did von Neumann's research come in? Anyone recognize something? Something with computer hardware? Well, it turns out that most of us use almost exclusively what is called the von Neumann architecture, which is a way, it's an architecture for building computers where we have a processing unit, a central processing unit. These days we have several cores, and those machines are in front of you, 8 cores, for example, or 4 cores, I guess 8 hyper-threaded cores, 4 physical cores. And then there's a bank of memory from which those processors read. And he invented that architecture. He was a physicist, but he had a huge impact on computer science, and he also dabbled in economics and other fields. And one of the fields he dabbled in was modeling, and modeling physical systems, particularly using tools very much like this game of life, a so-called cellular automata. And he envisioned whole computers being built with that sort of system, as indeed they have been built since then. So the inspiration here is kind of the life course of cells. Cells live and they die, but they don't live and die in isolation. They live and die partially affected by other cells around them. If there's no other cells around them, it's a harsh environment, and they'll die more quickly. A cell might come into existence precisely because a cell nearby undergoes mitosis, for example. It divides into two, and that forms a cell in this place. So cells come into being because of the presence of nearby cells, and they go out of existence, say, in the absence of those cells. And this so-called game of life, these set of rules, reflect a stylized capturing of that in what's called a cellular automata. This cellular automata is divided up to discrete space, and that space is tessellated, so it's broken up into these equal categories, so that over time we have in each category, as I said, either something that's living or dying. But beyond that, this is a model in what's called discrete time. And this is a very different model of time than we've been using, okay? It's a model of time that involves not time divided up in a continuous way into arbitrarily fine bits, where things happen as fast as they need to at certain times and as slow as they need to at other times. We jump from the time things need to happen to the next time things need to happen. Rather, it's in fixed time steps. It's fixed lockstep. And we're going to be talking about this. And in fact, all cells here, conceptually, they update at the same time. Okay? They update at precisely the same time as each other. It's not that one updates earlier than the other. They go, the board's in one state, and then the entire board evolves to the next state in a way that only takes, and that evolution is purely defined by the last state. It's not that one cell goes first and that influences the behavior of the next cell, etc. Okay, we'll talk about that. It's deterministic. Despite what it looks like, it seems to be sort of random in its depiction. This is a purely deterministic system. What do I mean by deterministic? I want to make sure you folks understand that. What do I mean by this is deterministic? Yeah, and if I were to put it in the exact same state and run it forward, it'll always yield exactly the same results. Was that true for the previous models we've been looking at? No, we had stochastics, right? Now you could say, well, with the random number seed, it would be deterministic. Fair enough, but random number seeds are a way of capturing sort of pseudo-randomness. And the idea is that those models incorporated this kind of pseudo-randomness, these stochastics, which were, from a practical perspective, random. Here, it's all deterministic. All these rules play out with precision. There's no flipping of a coin involved. So we're not playing dice with this model, okay? And a further element to this model is the game of life. And one of the reasons it caught both the popular eye and the eye of a lot of computer practitioners is that it illustrates how very, very simple rules, almost the simplest rules you can imagine, can give rise to tremendous complexity, tremendous sort of variety, tremendous tremendous differences in terms of how things behave over time. You can get something that's very descriptively complex, very unexpected. It exhibits complexity, sort of surprising emergent behavior from only the very simplest of assumptions and of rules. And we'll be seeing what those rules are. Okay, so what are these rules? The rules, as I noted, are profound in their simplicity. Each cell is going to be viewed as surrounded. This says 4, it should be 8. Okay, that's a misstatement. It should be 8 neighbors. Okay, here we go. So each cell is surrounded by 8 neighbors, and living cells require some neighboring empty space as well as some proximity to living cells. So a living cell will continue to live if it's not too crowded and if there's at least some nearby cells. Okay, so if there's only 0 or 1 neighbors, it will die. It's too isolated. Okay. If it's surrounded by 4 or more surrounded other cells, it will die as well. It will live if it's surrounded by 2 or 3 cells. Okay. If there's 2 or 3 cells next to it, it will live. It has that nice balance between not being too crowded and not being too sparse, too isolated. Okay. So it will live if it has 2 or 3 neighbors, if it's already living. Fewer than 2 dies out because of isolation. More than 3 dies out because of crowding. If a cell is empty, it can come into being if it's surrounded by a sufficiently nurturing environment. Specifically, it'll come into being if it's surrounded by exactly 3 cells in the cardinal directions in north, south, and northeast, southeast, northwest, southwest. Cells have no mobility. They live and die in the same location. They never move. Okay. Okay. I mentioned the different neighborhoods. This is going to be an 8-person neighborhood. We're going to have here, if you go to main, for those interested in seeing how this works, and you go to the population here, you'll find a population of cells, and you'll find there's 10,000 cells there. 10,000 because it's 100 by 100. Okay, a population of 10,000. And each cell keeps track of a couple of features. Number 1, is it alive or not? Number 2, what are its neighbors? And number 3, on a temporary basis, how many neighbors are around me right now after sort of some scan, okay? And initially, there's a 10% likelihood that a given cell will have a 10% probability of being occupied. 10% chance. Where's that set? Here in alive, it flips a coin with a probability of 0.1 as to whether it's live or not. Okay? True means it's live. Otherwise, it's false. Okay? So if you wanted to examine this with a lot more cells, and you wanted to do it in a hard-coded sort of way, you could always go there and you could change it by opening up cell here, change it so that it starts, let's say, at 0.5. This is not an advised way to do it from a software engineering perspective, but just to illustrate how that worked. Here we go. Now we have an environment where we have cells in much higher density. And if we run that forward, we'll get something getting much more similar to what we saw originally in terms of its dynamics, okay, in terms of its sparsity. So it's in some sense self-governing. You know, if you start it too crowded, it will come back to this more sparse. If you start it with sparse but enough basically viable elements, it will build up to something that's a little bit more crowded. Okay, I'll leave that changed for the moment. We have neighbors accumulated within this and that are gathered and then used. And then we have a count of the number of live neighbors around. And you'll notice that up in the upper left of the cell, there's actually a little square that basically indicates is this that changes the color. It determines the color. If it's alive, it's red. Otherwise, it's this background color called lemon chiffon, I'm told. Okay. So, ladies and gentlemen, the core logic here captures what I talked about just a minute or two ago, right? It captures this this exact set of rules that we talked about. So, capturing the fact that a given cell lives on if it's not too isolated, not too crowded, and a new cell is born only if it's surrounded by exactly 3 neighbors. Let's go see where that's captured, right? So if you go to cell and you go to the properties of cell, you'll go to an area that reflects the fact that this model evolves in steps, in this lockstep way, defined steps. So instead of putting this in an event, we put it instead associated with the cell itself in the so-called on before step and on step. And there's a reason for this computationally. Why those are broken up. So if we go to cell here, and we go to agent actions, you can see that on before step, we go and we perform some action, then on step. So on before step is basically executed before any updates occur. Each cell undergoes on before step, and it basically provides the way of that agent gathering the necessary information it needs to undertake, to update itself in the on step event. So on before, all the information needed before any other cell is changed, and then on step goes through each cell and has them each update according to that information they've squirreled away, that they've saved away. Okay? What information do they saved away? Who can tell me? Reading this code, what is this doing? I would write the code more elegantly, but what is that doing? What simple task is this undertaking? Yeah, counts the number of neighbors for this cell which are alive. That's the information it stores away when this n alive around. And then when it comes time to actually update the cells, what is this rule doing? I wouldn't have written it like this because I think it's unnecessarily obscure, but it's correct. So what is this rule doing? By the way, you can't see a key operator in here, so I'll pull it over. What is this rule doing? Who can unpack the Boolean arithmetic? Suppose the cell is dead. Suppose the cell is dead, or there's nothing there, I should say. The cell is empty. Alive will be true or false? False. So this whole thing will be what? False. The only condition under which that cell will become alive is if what? Yeah, there's 3 neighbors around it that are living. By contrast, suppose this cell is alive currently. This location is alive. This is called cell. I would have called it patch, whether it's occupied or not. But suppose the cell is alive. Under what conditions will it stay alive? It'll stay alive only if what? Notice it's alive and this has to be true. So we'll stay alive if what? Colloquially, how would you say this? 2 or 3 neighbors. Yeah, 2 or 3 neighbors. And this other, you might think this other condition will change it, but it doesn't. I mean, this is just furthering. If it's 3 neighbors, it's alive. Okay? So this is kind of the rules for updating that cell. Again, I think it's a little bit obscure, particularly for teaching, the way they implement it, but it's correct. And some of you may delight in its Boolean logic. Okay, so ladies and gentlemen, you know, enough on some of the details here. I want to talk a little bit about this model of time. Okay, previously we've been dealing with continuous time, and in fact, most of our models, including next time, we're going to deal with continuous time. And in fact, I'm going to share before the day is out, actually before office hours are out, depending how the traffic is. I will share with you a continuous time version of this, where agents don't all update in lockstep, they update in continuous time. What that means is that things happen at kind of their natural time, and as fine and time as needed to delineate different times. So A can happen before B or after B. It very rarely happens at the same time exactly as another event B. So 2 agents, one might, in continuous time, one might go before the other, or vice versa. Only very rarely would they go at the last time. Okay, they're not updated typically at the same time. One updates when it needs to update the other, etc. A very natural thing because it mirrors how time works in the world, and it turns out that it simplifies a lot of our thinking about the world to be able to deal with things that sort of mirror the continuous nature of time in the world. But in these models, this one and the next one, which will incorporate mobility, we're dealing with synchronous time. We're dealing with discrete time. And once again here, it means discrete means it's countable. There's defined, distinct time steps. So we're in time step 1, or time step 2, or time steps 3, 4. And hence, this terminology on before step, on step. Those are the time steps when it's evolving. Okay. Now here, all agents change in lockstep is the conceptual model. all agents change. We have a current state of the system, and it's perhaps best illustrated here by doing something like this. I'm going to pause it, and then I'm going to run it here a single step forward. Okay, here we go. It's stepping. Okay, come on. Okay, I see. So I need to update it, run. Okay, what I'd really like to do is to do this run for one time step here. Okay, here we go. Boom, and you could see it run for one time step. The entire space updates at once. The entire space is in one state. All the agents figure out what they're going to be in the next state simultaneously. So none of them have updated yet. It's all based on the current state. And now it goes to the next state. They're all looking at that state. They're all up figuring out what they're going to do in the next, and then it updates the next. So they're all going in lockstep, all at the same time. Okay? This is very similar to what we're doing in system dynamics, where we didn't have to worry which stock updated before which. We just said, this flow depends on that stock, this other flow depends on this different stock, and it took care of capturing the fact that the stocks were basically all updated at once. Okay? So it turns out you can enable this. I'm not going to go into it in detail, but it turns out that you could go to main and you can enable steps here in main, and that will enable discrete time, enable the presence of these steps. Okay, and we saw before how the logic operated here, and I'm not going to dwell on that because I want to get on to more important things. Finally, for anyone hoping to figure out how it works, within the initial startup of the agent, it gets its neighbors. It goes and obtains its neighbors for efficiency reasons. Okay, so let's go run this model. All right. Here we're running it, and what we'll notice. Well, can anyone tell me, what do you notice as happening in this model? Tell me some interesting broad patterns you see from running this. I recognize each run is a little bit different. This model is set to be set up initially in different states. If you go look at randomness, oh, it's actually, okay, it's actually a fixed seed. So every time it will be set to do the same one. We could set it to be a random seed, so the initial state will be different each time. I thought it was already set to that for points of interest. But what features do you notice? What are some broad aspects of the sort of phenomenology, the features of this? Very simple rules about a cell living, only if it has continued to live, it has 2 or 3 neighbors. A cell being born, only if it has exactly 3 neighbors. What features come out of this? Tell me some broad regularities that come out. Yeah, there's certain locally stable states, right? Here's one of them, a block. Here's another. There's another that's sort of stable in a sort of evolving sense. It's sort of in a dynamic equilibrium. It's in a periodic orbit. It does one thing, and then it does the next, and then it goes back, and then it does the next. It's kind of like in state space when we were talking. I don't know if anyone remembers, but at one point I mentioned situations in state space where we can have a fixed point, and then we can have sort of periodic movement around that fixed point. In fact, we saw that for the gophers and coyotes, right? It's sort of, you have this regular waveform coming out of it. Okay, so those are great observations. What other observations are there about this? Does it always obey the second law of thermodynamics? Does it always become more entropic over time, more disordered? Does it ever become more predictable and not less predictable over time? Let's try this, right? Let's try running the model. Does it ever, over time, get into a more ordered state? Yeah, it actually does. It can get into these kind of low energy states where it's quite predictable from an earlier state, which was quite unpredictable, right? Quite entropic, quite hard to predict. It can settle down to a state that's more regular, more ordered. Okay. What other features come out of this? Yeah, they can travel. You can have collective behavior that moves, collective patterns that move, even though the individual cells don't move, right? You can have, and sometimes you get it by clicking on them, you know, with the right components. You can create these little spaceships that zip around, right? And that actually can move some distance in space. Those are collective phenomena. Again, it's kind of like a wave. The little bits of water don't move, but the wave moves, and the wave can do tremendous damage by moving over time. So so a wave can have momentum. It's a collective phenomenon, much like a traffic jam is. Okay, what other features of it? Those are all good features. What other ones? Maybe it's addictive. Well, okay. Beyond that, yeah, they're segregated, so they're less coupled. Because when we get coupling, that's when things can start to get more complex. So that's good. These stable units are basically isolated. I like that point a great deal. Okay, so excellent. So this is a model that can elicit, in a technical sense, complex behavior, unexpected behavior, behavior you couldn't directly anticipate from the starting state will come out of this. But let me tell you a further fact, because you folks, many of you are computer scientists, I'll tell you another further fact. This model is Turing complete. This model is computational, or sorry, this set of rules is Turing complete. It's computationally universal. What do I mean by that? What do I mean by it's computationally universal? Anything that you could run on those computers in front of you, anything you could run on your laptops, anything you could run on your tablet or your smartphone, anything you could run on the world's biggest supercomputer can actually be run using this. Any program that can run there can be translated into a way that runs on this. This is a computer, ladies and gentlemen. Or this can be used as a computer. And in fact, long before you walked the face of the earth, and I might add, even long before you crawled it or creeped it, that's a technical term for baby's early motion. It's not a comment on your character. Long before that, there was generations of computer scientists, students young like you and with lots of energy, who spent untold hours running this game of life. This is, yeah, it was before Halo and grand auto theft and all those horrible things you have today. And people would run this model, and massive amounts of computer time were spent simulating games of life. Out of interest, to find interesting patterns that emerged, kind of like digging gold. You'd sift through things and find really wild patterns that emerge from it. And computing statistics, et cetera. It was said at one point that more computing cycles had been wasted playing games of life than had ever been run on running real programs, something like that. It was a really big thing for a long time. And there's still people who are sort of cultists of the game of life and will run it, and there's all sorts of fancy implementations will run in parallel or very, very quickly in large scale areas. But one of the lines of work that this led to was, in fact, some work by computer scientists to determine if the complexity shown here could be used to create capture computation at sense. And what the researchers built up, it was people like Gosling, I think, and maybe Greenblatt, sort of hackers at MIT. They built up structures using these different subcomponents to implement AND gates and OR gates and NAND gates. So they created digital gates, digital logic on this. And having created digital logic, they then built up from that state-based logic. So you could have flip-flops, and you could have adders and clocked elements, and they'd be clocked by these little things that shoot around and communicate. And from that, they built up whole computers out of this, which could compute programs. And they could give it a program, and it would compute, and it would show an answer. It would present an answer back. And through this, they basically showed that anything written for a Turing machine. How many people here have heard of Turing machines before? Okay, okay. I'm relieved it's at least a large fraction of the class. Anything that could be written for a Turing machine could be implemented with this. Anything that could be written for the computers in front of you could be implemented with this. This is a Turing universal computational mechanism. The rules here are sufficient to capture anything on any computer. And so if you really wanted to, folks, you could play grand auto theft on that game of life. Think about that. Okay. So this game of life was a milestone actually in computing and thinking about non-traditional ways of computing. But more than that, it was sort of a way that merged with public awareness of these sort of how simple rules could lead to really interesting behavior. More than that, ladies and gentlemen, computing pioneers, as computing challenges grew with traditional architectures, came to realize that this type of computation, distributed computation over a large space, could actually be useful. So you may think of this as kind of a weird variant with some arbitrary rules could be used to implement computers, sort of like how Danny Hillis, the founder of Thinking Machines, built computers when he was young on Tinker Toys. He did. You could do it out of this, but it's more than that. These sorts of cellular automata, because they're physically distributed, because they're created over a large space, for example, and because you have purely local connections between things. Each cell depends only on its neighbors. It doesn't depend on going to a cell way over there, way over there. It turns out that it's very easy to build simulators that simulate this in a scalable way, in a way that can be built to larger spaces, because you don't have to get things from one place to a very distant place. And so these updates can be very frequent and fast. And because it's distributed, you can get dissipation of heat, etc. So these cellular automata captured considerable interest as ways of actually implementing computation in a genuine sense. And when I was young, I worked on one of the earliest cellular automata machines, and was working on elements of the infrastructure for that. They remain of considerable interest in terms of computational mechanisms, and they have some relevance in terms of quantum computation. So this is a cellular automata, ladies and gentlemen. Each cell is in a discrete set of states. It operates in discrete time. It operates in discrete space. And very simple rules can give rise to surprising complex behavior. It is a stylized model. We see how a few simple rules give rise to behavior that not only is technically complex and descriptively complex, it is more than that, computationally universal. Okay, and it exhibits features that look random, even though it's deterministic, much as complex systems often do. So, ladies and gentlemen, a cellular automata, an automaton where each cell lives or dies in place, but we have collective behavior that move, for example. I'd like you to now open a different model, which shares many features, but has one key difference. Specifically, it incorporates mobility. So we're going to close this one, close the game of life. And I'd like you to open up here, under example models, something called Schelling segregation model. Okay? Now, the Schelling segregation model also has a storied history that dates back to the 1970s. But this work came out of ideas not by British mathematician Stephen Conway or John von Neumann, Hungarian and working in the States, but instead out of sociology. Sociology and economics, I think it might be fair to say. And it's to the work of, I believe the first name is Thomas Schelling, who's actually a Nobel Prize winner in economics. Okay, this was long before he won the Nobel Prize, as I recall. And he was interested in patterns of segregation and troubled by them. The fact that cities often have areas that are clustered. And in the US, it was predominantly African American and Caucasian Americans, often living in their own areas with limited interchange between them and limited opportunity to get to know each other and to develop collegial relationships across racial lines at the time. This was a time of great racial tension in the US, and he was interested where those patterns came from. And he had some ideas, and these ideas were first tried out in a way that really reduced them to their very basics, as good stylized models do. So his ideas were maybe some of these patterns, not all, maybe some of them result from decision-making on the part of agents on a very simple basis, on a basis of where they choose to move, or where they choose to live, and when they choose to move. So in order to investigate this, he didn't have ready recourse to programming expertise. Computers were more specialized items that day. It was hard to find programmers. So he brought out a checkerboard, game for checkers, right? Red and black squares. And he put coins on the checkerboard. And he used them to reason about, okay, suppose that we had individuals in these spaces. These ones were empty. These ones were occupied by an individual of this color or that color. And suppose that individuals, for example, preferred slightly to live near people like themselves. Maybe because they find it easier to communicate. Maybe because more of their friends or of their same background. Maybe it's because they have common tastes in terms of extracurricular activities. Maybe it's because they feel safer, or they feel more comfortable in neighborhood activities, or what have you. So he created a game of sorts, called the game, but it's not. It's dealing with a very serious issue, where essentially a given neighbor is situated in space, and once again, it's a two-dimensional space. It's a discrete space. So we have discrete columns and discrete rows. And in fact, like the last model we looked at, the game of life, it's in discrete time. Time updates all on lockstep from one time to the other. Okay, and here we have 100 columns and 100 rows, just like the others. And we have a person who is either satisfied or dissatisfied. And like the last model, on before step determines if they're satisfied, and then on step, if they're not dissatisfied and a certain outcome with a certain probability is true, they will jump to somewhere else to live. Okay, this isn't quite his original rules, and I have a different version. I might have a different version that actually influenced his precise rules. But here we have individuals. They're looking at their neighbors in space, and maybe you could tell me, under what conditions will this individual be satisfied? Take a look at that code. Many of you are computer scientists, and you should be able to tell me between the comments and the code itself what this code, the net impact of this code. Okay, so I am satisfied if there is no neighbors at all, Okay, that's different from that last model where we needed cells. I'm also satisfied if what? I don't like the exact conventions by which this code was written. We could put parentheses around this. That might help guide your eyes. I'll be satisfied if what? Use the threshold. Yeah, some fraction threshold. Okay, so ladies and gentlemen, suppose, so I have a certain threshold that I want of neighbors to be like me. I want at least 25%, say, of the neighbors to look like me. And if I don't have at least 25% of the neighbors that look like me, and there's any neighbors, and there are any neighbors indeed, then I won't be satisfied. To be satisfied, I need the number of neighbors that are the same color as me to be greater than or equal to this threshold, say 25% times the number of neighbors. So if I have 8 neighbors and only one of them is the same color as me, I won't be satisfied. Okay, because then fewer than 25% of my neighbors are my color, and so I won't be satisfied. If I have 3 neighbors of those 8 who are my color, then it will be satisfied. I have more than 25%, greater than or equal to 25% who are my color, and I'll be satisfied. If I have 2 of those neighbors, I'll just be satisfied. Does that make sense? So this n same counts up the number of people like me, and I multiply it. I check if the number of people like me that are around me are greater than the total number of people around me times the threshold. Okay, so that's the rule. So, and then if I'm satisfied or not, and then if I'm not satisfied, I have a 30% chance of moving the time step. Okay. What sort of behavior might you expect to come out of this? Oh, I should have emphasized, this is my problem. You'll notice here we have 8 neighbors as well. Okay, 8 neighbors around me. So ladies and gentlemen, what sort of behavior do you expect to come out of this model? So think about it. Each person has some threshold. Let's suppose we set the threshold at 25%. What sort of behavior might we expect to see? So if I'm not satisfied, I move to another random location with a certain probability. So what do you think will happen over time? Okay, we may get clusters of individuals. If we sort everyone in random locations initially, and then we run it, we might start to see clusters. Why might we see those clusters? Give me a sort of a narrative reason. Give me a reason why those clusters might form. Why might those be generated by this model? Why might they emerge from these rules? We didn't tell them to the model, but why might they come out of it as a collective property and an emergent property of this model? Good. Good. And okay, let's explicate that a little bit more. So it's a good start, excellent start here. So I might, if I'm in an area that has too few people that look like me, I might move. And I'm not guaranteed to get to a new area that has enough people like me. So I might move again, and I'll keep on moving until what? And find enough people who look like me, and then I'll tend to stay there. And so you'll get this kind of aggregation over time of these clusters. So let's go run this thing. So that's kind of what we think. How would it, as we raise the threshold, how would it change? Let's suppose I raise the threshold from 25% to 50%. How would that change things? Maybe the lumps will be bigger, yeah? Okay. 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 How if we raise it to a very, very high level? Okay, so it might be really hard to get that cluster going, and because they won't settle for anything less than exactly uniform population, and so they're going to be searching all over and not be able to find something adequate except maybe being alone, something like that. Okay, so these are good dynamic hypotheses about what we might expect, but here we have a computer to do the job for us. So what I'd like you to do is to go here, and I'd like you to run the model here, okay? And I'm actually going to drag it down here to something like 25%. You can actually probably do a better job with dragging it here. And I'm going to, and it's too bad because I'd like to, I could pull down this and I'll put it down the time scale. So I pulled this down and did time scale. And I'm going to run it at full tilt. So this is 25%. Is there clustering there? Can you tell me? Is there clustering? Yeah? Do you see clustering? Maybe it'll help if I go here. I'm going to go into, I think it's window, and I'm going to allow for zoom. Boom. Okay. There we go. And I'm going to go and bring this down before it settles down, bring it down to this. I'm going to keep it at about 25% here. Hey, come on. 24% fine. And I will do this, and I'll run it full tilt. Is there clustering? There's some clustering, right? We could use entropy measures or something to characterize this, but you can see that at a qualitative level, there's some clustering. You agree? It's more likely that a given thing will be surrounded by things of its same color or blank than things of the opposite color. Okay, so suppose we raise this to something like closer to 50%. Okay. Now I raised it over 50%. Okay. Now we're seeing bigger clusters form, right? You notice if I bring it down, nothing changes. Why is that? Why is it if I bring this down to lower amounts, nothing changes? Yeah, if they're less demanding, if they're satisfied with a looser criteria, just 16% of my neighbors rather than 56, I'm perfectly happy where I am too, so I'm not going to move, right? This was from 56%. I brought it down just to make that point. This was up around 56% earlier, right? Now I'm going to 66%. What do you see is happening as I raise that threshold? What's going on? Yeah, the clusters get larger. Is it just that they get larger? Yeah. So they're getting kind of smoother. More than that, they're also getting surrounded by what? What are these lemon chiffon things? Yeah, they're empty space, right? Empty space. Okay, here's 76%. You notice it's actually getting a little bit smoother, a little bit less surface area here. Okay, now I raised it to 86%, and now it's hopeless. They're searching for people who are only like them. They only want to live with people who are like them. They're not satisfied unless everyone is like them at a practical level, because basically we only have 8 neighbors and 96%. To get 96%, we need all 8 out of 8 of the same color as us. So here, these individuals around them, they will be dissatisfied unless everyone around them is their same color. And that is so unlikely to happen here that that it never converges. Okay. Meanwhile, we could bring it back down again to low levels, and we can notice once again this gradient as we build it up. So, ladies and gentlemen, this is collective phenomena. These are emergent patterns coming out of this. Very simple rules, but there's also threshold effects. There's effects with this set of rules, which are not exactly Schelling's original set, but a close variant on them. There's states where it gets totally disordered. And interestingly, those occur at when you're very, very demanding. And when you're demanding only a small bit, you can get a steady state, but it's also quite disordered. It's really once you start getting up here that people get so strong in their preferences that it starts imposing these sort of larger scale structures. So this is a model that's like the last one, stylized. It basically is asking the provocative question: if we have this very simple assumption about people's behavior, if we posited that people have a certain degree of preference, maybe it's a very small preference, maybe it's just, you know, they'd like to have at least 25% of the people on the block look like them, and we put them into an environment where they're willing to move. If that doesn't happen with a certain probability, that will lead to patterns of segregation that can be notable. Even with just 25%, we can see quite a bit of what we call sorting, quite a bit of clustering of individuals here. Not everyone is a glaring and racism or what have you, but you have people who are joining together because they have these slight preferences, and the slight preferences between many people accumulate to yield big patterns in terms of clustering. And those patterns become more and more pronounced as those preferences rise. And of course, this model is powerful because it is stylized. It posits just these very simple mechanisms and asks, to what degree could they be used to explain high-level patterns of segregation, of sort of clustering? And the answer is, to a very strong degree, they could. To a very strong degree. Now, in a real-world situation, one could seek to complement this model by additional things. One of my colleagues at Michigan works with this model to combine it with more realistic types of decision-making, to layer in just a little bit more realism in decision-making and see how it affects things. Another thing you might do is capture, there's a feedback, right? If you grow up in an area that you only surrounded by people that look like you, maybe you will carry a stronger preference in adulthood for that. And so you may get, over generations, successive movements toward additional segregation, additional grouping on the part of individuals. We could move this model in a direction of having additional processes operating on these agents, processes involving formation of relationships over time, or familial connections which might occur across groups or what have you, that might counteract some of these effects. So a very, very simple model, very powerful in what it can demonstrate, the emergence of these patterns even at small areas of preference, but fundamentally one that is designed not to talk about Chicago, about Detroit, about Los Angeles and the particular patterns there, but rather to illuminate how very simple features of human decision-making or decision-making could lead to broad patterns just by themselves. In fact, they're probably mixed in the broad milieu with other types of issues as well. So another stylized model in discrete space in discrete time, and one with a powerful result as the outcome. Here, not computational universality, but very, very large-scale patterns emerging from very, very simple, plausible rules. So sometimes what you see with models like this is a set of simple rules that capture undeniable features of the world. As we call them sometimes, stylized facts about the world. They're features of the world that are very basic, almost beyond dispute. And a model like this, you capture just a few features and you see what the implications are. An example which I have seen investigated in this class and past projects, for example, is trust. I proposed that. It's an interesting issue. So I could list some stylized facts about trust. Trust takes a long time to build up between two people, but can be easily broken between people by an adverse incident. You know, it may take a while for me to develop comfort in working with you as a work colleague, trusting you with my money. And if I find there's been some funny business and some of that money has been diverted, that trust can be broken like that. So there's an asymmetry there. If A trusts B and B trusts C, then often A ends up trusting more C. A is more likely to trust B if B at least doesn't distrust A. So there's a sort of reciprocity there, or reciprocal feature of it. There's many aspects of trust that we could reason about, and that would be an example of a very simple stylized area where we could build up a model that captures just a few of those features, and you see what the implications are. So stylized models are often used together with these stylized facts, which capture features of the world in a way that we capture almost a caricature. Surely you folks have seen political cartoons. You know, maybe politicians with giant chins, or distended hair sticking up in strange directions and colored with bright colors. Maybe you've seen political cartoons with an individual with giant eyes. And those aren't exact depictions of that person, but they bring out certain features of the situation that are notable in a way that's very easily recognized. And stylized models are a little bit like that. My colleague Carl Simon at Michigan likes to refer to them as almost caricature models. So they capture a few essential features of the situation and let us reason through their logical implication over time and over space in this case. If we have just these simple rules, what are the implications? It's hard to do purely in our head in a quantitative way. We captured some elements of it, reasoning about it, but it wasn't until we ran this model that we saw the impacts that we could be more specific in our understanding. It wasn't until we ran that game of life that we recognize certain features of the situation, stability, and the fact that we could be these moving patterns, even though each cell is fixed, and the fact that you can get, bursts of outcomes and then sort of going more to order, and you can get these features that are computationally universal. To really explore those things, ladies and gentlemen, we need a computer. We need a simulation. So simulations, ladies and gentlemen, you may recall, are learning tools. They're learning tools to help us think through the impact of our assumptions, to reason through, if I have these rules, what's their collective implication for the dynamics of the system? What patterns are going to emerge from that? And by implication, often we ask how consistent are those patterns with what we see in the world? So these are some stylized models incorporating space and incorporating discrete space and discrete time. Next time, we're going to make a change to a couple elements of that, but keep the spatial embedding. We're going to look at spatial embedding, but in the context of continuous space, GIS space, latitude, longitude. In the context of geographical information, in the context of continuous time, we're going to look at mobility there and having agents moving between different spots, and spending time in a way that's shaped by the nature of that environment. And if time allows, being affected by that environment or affecting it in turn. So that's all for today. Thank you very much for your attention. As always, I'll hold office hours, and I look forward to covering on Thursday the both elements of the take-home exercises. Thanks very much.